Good day, class. Today we're going to be talking about flip flop, particularly focusing on the SR flip flops. So we have the NOR, the NAND, and the clocked SR flip flop. We're going to be starting with the NOR flip flop for now. So the NOR flip flop is an active high. I will explain that. So this is the NOR flip flop. It's an active high latch. So this is the NOR gate latch. This is a truth table or the function table, and this is the block symbol for the NOR latch. So how does the NOR latch work? Set, the function of set is to set q to 1, and the function of reset is to set q to 0. So you can see here, when set is 1, q is 1, when reset is 1, q is 0. And when both of them are 0, there's going to be no change at the output, and when both are 1, that's an invalid output. Why? It's because set is trying to set q to 1. At the same time, reset, also 1, is also trying to set q to 0. This is going to be interchangeable between 1 and 0, 1 and 0, and the output of that system won't be known because it just keeps switching between 1 and 0. So now, the reason why it's called active high is because set will carry out the function of making set here will carry out the function of making q1 when it's high, when it's at 1, and reset will carry out its function of making q0 when it's high, that is when it's 1. That's why it's called an active high. You see the difference between active and active low when I explain the NAND latch. Now moving on to a question. It says assume q, that's the output initially, q equals to 0 initially, and determine the q waveform for the NOR latch input. So we're going to be using the NOR gate table for this. So now, at every point where I see a change in my set and reset, I'm going to draw a line there. So you can see, at every point where I see a change, I'll draw a line there. The initial version of it can be seen here. So because it's at these changes that you can record whether it's 0 or 1, whether set has changed to 0 or it has changed back to 1. So now we're going to draw our output. So for the output q, initially, they said initially q is 0 from the question. So q is just going to be 0 till it stops here. So this is the first change. At this change, what happens? Set became 1, reset is 0. We look at the table. So let me just use another color for this. It's green. So now set is 1 and reset is 0. When we look at the table, we see it here. Set being 1 and reset is 0. What's the output? Q is 1. So we're going to make Q 1. So this is 1. Next, then we're going to start at this part. Next, there's a change. Set is now 0 and reset is also 0. At that point, what happens? There's no change. So we're just going to continue to stay 1 to reach the next change. At this point, what is reset? 1 and set is still 0. So when we look at the table, we see when set is 0 and reset is 1, Q becomes 0. So this is going to toggle down and become 0. Next, we're going to see here set is 0 and reset is 0. There's no change. So we keep going. Next here, we're going to see set is 0, reset is 1. You can see it at this point. Q will become remain 0. Next, at this point, you see it set is 0, reset is 0. There's no change. Now at this point, set becomes 1, reset becomes 0. That is, at this part of the table, Q becomes 1. Going to go up. And now lastly here we're going to have set as 0 and reset as 0. That means there is no change. So it's going to keep going. And this is just the output waveform for a NOR gate. Thank you for listening. So hoping you understood the NOR gate, we're going to move on to the NAND latch. So the NAND latch is an active low. And let me explain what that means. It means when S is 0, set is supposed to, what we learned from the other topic is that set is supposed to change Q to 1 when it's high, right? But at an active low, set can only perform the function of making Q1 when it is low, 0. That's why it's called active low. So you can see here in the diagram, when set is 0, it performs the action of making Q1. And when reset is 0, that's when it can perform the action of making Q0. So that's how the NAND latch works. Now let's look at an example. Assuming q is equals to 0, determine the q waveform. Again, we're going to draw our line as where we see any change. So I'm going to draw a line here. That is all. That's all the changes. And just to give us a neater diagram, this is what it's going to look like. So we're going to determine our q output form. So this is the table we're going to be using beside here. So for the first batch, they say q is initial equals to 0, so we start with 0. Now at this point, let me change the pen. Okay, so q is equals to 0 initially. Now next we see set is 1 and reset is 0. That is seen here. That means q will still remain 0. So now for the next line, we have set as 1 and reset as 1. There is no change. That's all. There's no change, sorry, not it changes. There'll be no change here. So it's keep being 0. Next, we have set as 0 and reset as 1. You can see that on this line. That means q will be 1. You're going to toggle it up to 1. I'm going to stop here. Now set is 1, reset is 1. There'll be no change according to the table, no change. So we're still going to continue to reach here. Now there's another change. Set is now 0, reset is 1. That means q will still remain 1. Now here set is 1, reset is 1. That's at this point there'll be no change. So still going to keep going with 1. Next, at this line, you can see that set is 1, reset is 0. Sorry, set is 0. That is at this point q becomes 0. So we drop q down. And now we know here set is 1, reset is 1. That is just no change. So it's going to continue. And this is our output waveform. Now, hoping you understood the NAND flip-flop, we're going to look at the clock SR flip. The clock SR flip-flop, just as the name implies, depends on a clock signal. So I'm going to explain this to you. A clock signal can be activated. So here the clock is activated by PGT. That's a positive going signal. You can see when it's going up. And here the clock is activated by NGT, negative going transition. So that's when the clock is going downwards. This is also called positive going transition. So in the case of this SR clock flip-flop, we're going to be working with PGT, that is positive going signal going up. That's what we're going to be working with for this particular example. So now we're going to look at this example. Now the key word about this one is dependent on the clock signal. So we're only going to draw our lines and specifically dependent on PGT, a positive going transition of the clock signal. So when we're going to draw our lines, that's where we see an upwards arrow. You can see. Why? Because this particular flip-flop is dependent on the clock signal. Now this is just a much neater diagram of it. This is it. And this is the table beside it. So let's start drawing our output Q. Now this is only focused on the positive going signal. So assuming the initial of Q is 0. So it's going to go from 0 to here. And make use of the green marker. Okay. Now at this point we only take into consideration what we see in the S and R immediately after the positive going signal. Then we ignore every other thing till we get to the next positive signal. Let me show you. So S here is 0, R is 1, R is 0 as well, sorry, and that means no change. So we're going to keep going with no change till we get to the next PGT, positive going signal. Then now immediately after this positive going signal, what do you see? S is 1, sorry, excuse me, S is 1, R is 0. What does that tell you? S is 1, R is 0, look at it here, Q is 1. So Q is going to go up to 1 and it's going to remain 1 till it gets to the next PGT. Now next, after immediately this PGT, what do we have? S is 0, R is 1. Where do we have that? Here. Times Q will be 0. So we're going to bring Q down to become 0 till it reaches the next PGT. Now, immediately after this PGT, what do we see? S is 1, R is 0. Let us see S is 1 and R is 0. That's here. Q becomes 1 again. So we're going to toggle it up till we get to the next PGT. At this point now, S is 1, R is 0. What do you see here? It means Q will still remain 1. And this is what we have for the output waveform. So thank you for listening, and I hope you understood. Today we just tackled on the three types of SR flip-flops we have: NOR latch, NAND latch, and the clocked SR flip-flop. Thank you for listening.